We're going to cover section 4.4 in the videos today on the mean value theorem. And the mean value theorem is a really important theorem that underpins a lot of the formulas and theorems that we're going to use throughout the rest of the semester. So we're going to take a little bit of time today to go over it. It looks really confusing and complicated written down like this. So before I read through it, I'm going to illustrate it to you over on Desmos. If you look under the resources for the week, I have posted 4 Desmos files that I'm going to go through that are going to help us to understand what the mean value theorem is telling us. So here's our first Desmos file linked under the resources for the week. I've got a function graphed there, and then I've got a file that says points A and B. So the mean value theorem kind of invites you to pick any two x coordinates, A and B, and find their associated points on the graph. And here I have those points graphed A and B, and I put the line between them because what we're about to say in the mean value theorem has a lot to do with slope. So what the mean value theorem says is that no matter what points A and B that you pick on the function, you are guaranteed to be able to find a point C that's in between them. I'm going to turn on that point C. You're guaranteed to be able to find a point C in between them where the slope of the tangent line matches the slope of the line through A and B. So these points are draggable and you can play around with this. So if I move this point B and I alter the slope, this is telling you that you should be able to drag C around and find a point that has the tangent line parallel to the line AB, where they have the same slope, where the derivative at the point C is equal to the slope between the 2 points at A and B. Here's our second Desmos file, and it's got a different function on there, but the same idea is holding, that I have the points A and B, and you can drag them around anywhere you want, and you're guaranteed to be able to find that point C that's somewhere in between A and B, where the tangent line, the red line, is going to be parallel to the green line. And this one actually has more than one. I can drag this C point up here, and I'm still between points A and B, and I can find another spot, if it'll let me drop it in the right spot. There we go. Another spot where the tangent line is parallel to that line through A and B. So it guarantees you that you're going to find at least one. It doesn't tell you how to find that point, but it does guarantee you that such a point exists. Maybe there might be 2, maybe there might be 10. The mean value theorem has 2 conditions to it, and I'm going to illustrate those to you in the next 2 Desmos files. Number 1, the function has to be continuous on the interval from A to B. So if I find points A and B, if there's a discontinuity between A and B, like there is here, I've got this vertical asymptote at 2, then the mean value theorem does not guarantee that you can find that magic point C. So if I turn on C and I'm trying to slide C in between A and B, where I can get that same parallel slope, you're not going to be able to do it. You can do it possibly if you go outside the bounds of A and B, but look at this. This point C always has a negative slope tangent line, and that line going through A and B has a positive slope. So it's actually impossible to find that magic point C between A and B where you get a parallel tangent line to the secant line through A and B. And that happens, this falls apart because of that discontinuity at x equals 2. The second condition for the mean value theorem is that the function has to be differentiable on the interval from A to B in order for this magic number C to come into existence. And this function is not differentiable between A and B the way I have it drawn here, because we have that cusp at x equals 3. So we know that the derivative doesn't exist at 3. And again, if you turn on point C and you try to find that tangent line that has a matching slope to the line through A and B, you're just not going to be able to do it. And that's because of that spot where f is not differentiable. If you scoot point A past the cusp, where the function is differentiable between A and B, you actually will be able to find that point C. So now when I slide C between A and B, I'm able to find that spot where the tangent line goes parallel to that line through A and B. So now that we've been through some examples on Desmos, hopefully this will make more sense when we read it. So we have, let f be a function that satisfies 2 things. These are those 2 conditions I talked about at the end. F has to be continuous on the interval A to B, and it has to be differentiable between A and B. And if those 2 things are satisfied, then there exists at least one number, possibly more. There exists at least one number C between A and B, such that f prime of C is equal to f of B minus f of A over B minus A. And notice what that formula down at the bottom is saying. This f prime of C, that's the slope of the tangent line. At x equals C. That was that red line, that red tangent line to the function in those Desmos files. And then this over here, f of b minus f of a over b minus a, that's the y2 minus y1 over x2 minus x1 rise over run slope calculation between A and B. So this is the slope of the line through the points at A and B. So that's going to be the point A, comma, whatever the y coordinate is there, and B, comma, whatever the y coordinate is there. So in the next video, I'm going to do a couple of examples for you finding this magical value C, or explaining why we can't find it if we don't satisfy those two conditions at the top.